And excuse me for just a minute while I take care of some stuff. So we'll go over the daily 2 first, all right? In a moment. Okay, so I'm going to share the screen and we're going to go over the daily 2. And the first one was 2 negatively charged rods are brought near but do not touch the ends of a neutral conductor. What is the charge in regions A and B? All right, so remember the rules for charge movement. It's the negative charges that move, and they move towards a positive charge and away from a negative charge. Well, we have negatively charged rods brought near the end. So let's just talk about region A for a moment. The negative charges in region A will be repelled by the negatively charged rod, and so they will move out of region A. All right, they'll be repelled away. Likewise with region B, the electrons in region B will be repelled by this negatively charged object. So they're going to go away from charge A and away from charge B. When they leave region A, when the negative charges leave, that will cause region A to have a positive charge. Likewise with region B, when the electrons leave, the region B will have a positive charge as well. So the answer to this question is both regions are positive. Okay, both regions are positive. The center region would be where all the negative charge accumulates. So the center region would be negatively charged. All right. Okay, questions, comments on that? All right, well then let's go to the second one. Okay, when 120 volts of potential difference, and potential difference is the fancy name for voltage, is put across a certain resistor, a current of 2.4 amps flows. What is the resistance of the resistor? All right, I'm gonna stop sharing. This is an Ohm's law problem, and the simple version of Ohm's law is V is equal to I times R, where V is the voltage, I is the current, and R is the resistance, okay? And so if I want to solve for the resistance, then I'm going to divide, all right, I'm going to divide each side of the expression by I. So I'm going to divide each side by I. Okay. And I's cancel out, and I get R is equal to V over I, all right? And then I'm going to insert my values, 120 volts divided by 2.4 amps. Okay, and the number 120 divided by 2.4 turns out to be 50, and I get 50 volts per amp. Okay, and volts, oh, by the way, volts is named after a guy by the name of Alessandro Volta. He was an Italian, and he invented the battery. He was the inventor of the electric battery in the first decade of the 1800s, okay? So they named the unit of potential difference after the guy, volts, okay? Amps is short for ampere, and that's a French guy, André Ampère, who did a lot of really good work in the 1800s in the area of electricity and magnetism, okay? There's a Ampere's law that has to do with magnetism named after this guy. So, and then they took this unit for what ended up being called resistance, and they named this after a German guy by the name of Georg Ohm. So this has been called, the unit of resistance is the ohm. All right, so it's 50 ohms of resistance. So, and the symbol for that is the Greek letter omega, which looks like an upside down horseshoe. This is actually uppercase omega. Greek letters have uppercase and lowercase, just like our alphabet. That's a capital, up and uppercase omega. All right, so there you have it. All right, so the ohm has been defined as a volt over an amp. So you put here's my units joke for this. You put an Italian guy over a French guy, and you get a German guy. Okay, there's my units joke for that. So that's how an ohm is defined. All right, and there's your ohms. That's your basic Ohm's law problem. Questions, comments on that? All right. Then let's go over Electricity worksheet 1. All right, so I'm going to share the screen once again. Share the screen once again. And instead of this, I'm going to get my toolbar and I'm going to, here's the answers to electricity worksheet 1. All right. Number one, for current to flow on a wire, 2 conditions must be met. What are the 2 conditions? They must be 1, they must be on a conductor, and 2, an energy difference must be present. Or in my PowerPoint on my notes, I said a potential difference must be present. All right, I want to make an analogy with this with marbles. Okay, so I'm going to stop sharing for a minute. And on my tabletop here, I have a little trough full of marbles. Okay, now this represents a wire. The plastic represents a wire, and the marbles represent electrons. Okay, now there are 2 conditions must be met. For one, it has to be on a conductor, so the electrons have to be able to move. Okay, they have to be able to move, but electrons won't move unless they have a reason to move. And that's the second condition. An energy difference must be present. If they have a reason to move, then they will. And so I can give these marbles a reason to move by simply raising up one end of this PVC like that. And when I do, all of a sudden now there's an energy difference between the 2 ends, and the marbles will move to lower energy. They will be attracted. Okay, they're in a gravitational field, right? So once I give them an energy difference, they will go to a state of lower energy, or they will be attracted to the earth. Okay, all right. Well, similarly, electrons are on a wire. Okay, if electrons are on a wire, let's say this is the wire. Okay, and here's an electron. All right. Now, the electron is perfectly content to sit right there. All right. Unless you give them a reason to move. Okay. And once you give them a reason to move, then they will. And the way to do that is to put it in an electric field. Apply an electric field like that. And then the electrons will now be attracted to the positive end. And so now they have a reason to move. Okay. So those are the 2 conditions that must be met for current to flow. All right. Okay, let's go on. What's next? Definition of electric current. The unit for current is defined as the rate of flow of charge. Okay, the unit is the ampere, and it was defined as in the early 1800s to be a coulomb per second, a coulomb of charge per second. So, for example, if you were standing on the side of a river and the current is flowing, you might measure that in gallons per second. Okay, an amount of water per second. A coulomb is an amount of charge. So if you're standing on a wire, watching that go by, okay, watching the charge go by, an ampere of current is an amount of charge per second, a coulomb per second. And that's the definition for an ampere. All right. Number 3, voltage and current. What's the difference? Voltage is related to energy. Okay, difference in potential energy between 2 points, while current is related to amount of charge that passes a certain point. Okay, so if you're going to think of one word that you can associate with voltage, think energy. Voltage, energy. Current, amount. Think amount when you think of current. Okay, those are the words to associate with it. Okay, all right, moving on. Ohm's law. Okay, the formal definition is the ratio of the voltage across a conductor and the resulting current is a constant. So V over I, the ratio of voltage to current, is a constant. And I kind of don't want to take the class time, but what I could do is to have a resistor, like a light bulb in a circuit, have current run through it, like from a battery, measure the voltage, measure the current, okay, and then change the voltage, do it again, measure the voltage and current, change the voltage again by adding a battery, measuring the voltage and the current again, and then could do it one more time, 4 times, and then make a graph. And that graph would end up make a graph of voltage versus current. Okay, voltage on the vertical, current on the horizontal, and that graph would be linear. All right, and then you take the slope of that line, rise over run, and that would be a constant, and that constant has come to be called resistance. All right, so it's a linear relationship. All right, Now, to get rid of the denominator, it's more commonly written as V is equal to I times R, just to make it mathematically a little easier to deal with. Okay, so that's Ohm's law. Very, very, very basic to electric circuits. Voltage is, V is voltage, I is current, and R is resistance. Okay. Let's see. And then we're going to apply this. So the resistance of a certain appliance is 24 ohms. How much current passes through the appliance when it's hooked to 120 volts? Potential difference. And so now we're solving for current. So take Ohm's law, divide each side by R, we get V over R. 120 divided by 24 ohms yields an answer of 5 amps. 5 amps. Right. And number six, same kind of problem. A current of 4 amps flows through a wire when 120 volts is applied. Resistance of the wire. Solve for R. You get V over I. 120 over 4. 30 ohms. 30 ohms. Okay. All right. Any questions so far? All right. Next problem. Next question. What causes resistance? Well, before I answer this question, let's say you're flying at 30,000 feet in an airplane, like you're flying cross country, and you look out the window at the ground below, and the ground looks flat, right? Is it really flat? Well, no, but it looks flat because you're so far away. As you zoom in, that is, as the plane descends, all the way down, now you see the hills and valleys. Okay. Well, similarly, a wire, okay, or this aluminum rod, it looks smooth. It even feels smooth. But is it really? Well, no. If we zoom all the way into the atomic level, then we would see the hills and valleys, just like coming down in an airplane. And if an electron is traveling down the rod, okay, it's going to run into those hills and valleys. It's going to bore its way through or over, That is resistance. So it's resistance to flow. The electrons don't just have a free and easy path down the wire, like my marbles did down that plastic trough. No, they have to fight their way through stuff, right? And that has come to be called resistance. So resistance is due to collisions between conducting electrons and the particles of the conductor. Okay? It's caused by collisions. Now, different materials have different resistance. So what does resistance depend on? Okay. Well, for one thing, it depends on the type of metal. All right. It depends on the type of conductor. And the resistivity is a word that is a measure of how well it conducts. Okay. And different metals conduct best and or conduct better than others. And the best one is silver. Okay. Silver is the best conductor. So why don't we make all of our wires out of silver then? Well, because silver is expensive, okay? Fortunately, copper is the second best, and there's a lot of that around, okay? Although it's not as cheap as it used to be, but there's a lot of copper around. So we use that in our wires, okay? There's a lot of it. The third best is gold, and that has advantages over silver and copper, okay? If you leave silver out, exposed to air, so if you have silverware, I mean real silverware, and you leave it sitting in the drawer for a year, it'll get black. The outside of it'll get black. It'll tarnish, and that tarnish is silver oxide. Okay, silver will react with air to make silver oxide, and that's tarnish, and you have to polish the silver by rubbing off the tarnish. Okay. Copper also oxidizes. Have you ever seen a penny that's green? Okay, that green stuff is copper oxide. It oxidizes with the air, right? And that the oxide of those metals doesn't conduct. So the conducting properties of the silver and the copper are degraded by oxidation. All right. Now you can guard against that by, for example, wrapping the wire in insulation to keep it away from the oxygen in the air. That helps. Okay. Gold, on the other hand, doesn't oxidize, right? That's why you can have jewelry that's made out of gold, like a gold ring or something, and it'll years and years and years and years and years later, after being exposed to the air, it's still gold because it doesn't oxidize, right? It doesn't react with the oxygen. So if you're going to have exposed circuitry, okay, you might want to have gold as circuits. Of course, gold is expensive, so you can't do that a lot. But exposed circuitry, some circuitry that's exposed is gold. The conducting is gold because it doesn't oxidize. All right. The fourth best is aluminum, and aluminum is used in transmission lines. Okay, oftentimes thicker than this because it has to carry a lot of electricity. That's also open. There's no insulation on those wires. It doesn't oxidize a lot. Okay, aluminum doesn't oxidize very much, and it's also very light. So you don't want to. They don't put insulation around the wires, otherwise they would be too heavy. And if they got ice on them and snow on them, they get so heavy that they would break. So there's no insulation on those high on transmission lines, on the wires and transmission lines. All right, don't touch it with something like a ladder, or you're going to get electrocuted, and sometimes squirrels. Yeah, Henry, go ahead.
Yeah. So what do you need to do to make one of those materials become a superconductor, like with almost no resistance?
You have to cool it down to near absolute zero, because, and to do that, you use liquid nitrogen or liquid oxygen or something like that. Superconducting is a special property of certain materials, and they don't even have to be metal. Some of the better superconductors are ceramic and types of porcelain. And what happens when it gets very, very, very cold, and I'm not sure the details anymore. I used to know it many years ago, but I don't anymore. Don't remember. But there are certain properties where the material actually loses all resistance. I mean, the resistance goes down to zero. Okay, and so as long as it's kept below what's called the critical temperature, then the resistance goes down to zero, and the electrons can move without any resistance at all. And they can use that to actually magnetically levitate things.
Does that mean that they're moving at the speed of light, or
No,
they can?
they're not moving at the speed of light, although they're moving very, very quickly. The only thing that to move at the speed of light, you have to have zero mass. I mean, zero mass. Anything that has even a tiny bit of mass moves at a speed of less than the speed of light. So, and electrons, they don't have a lot of mass, but they have some. So they're not moving at the speed of light, although they are moving very, very quickly. They're moving at a certain percentage of the speed of light. I don't know, 10%. To the answer to that one, I don't really know. I know they're not moving at the speed of light, but they're moving very, very quickly indeed. It loses superconductivity is a special property of certain materials, not all, in which once you get them below a certain critical temperature, and it's a very, very low temperature, tens of kelvins or something like that, very, very close to absolute zero. They lose all resistance. The resistance goes down to zero. In order to achieve that, you have to cool them down with liquid hydrogen, or not liquid hydrogen, liquid nitrogen or liquid oxygen or something like that. Okay.
Is that why we came out with fiber optic cables? Because it completely removed or almost removed that, or the need for resistance, or removed resistance?
Would you ask that question again? I missed the first part.
Is that why we developed fiber optic cables with lasers and light, so we got around that?
Yeah, because in the old days, and when I'm talking the old days, I mean like 50 years ago or more, they used to carry signals by copper wire, like between telephones. But the resistance between the copper wires presented a problem. And so they developed the notion of fiber optics, which does not use copper wire. They actually use radio waves inside of fibers to carry the signal. And I hope to get to that before the year is out. Okay, I hope to talk about fiber optics and the science behind them and why they're beneficial and stuff like that. That's in our light unit, because in fiber optics, it's really carrying a type of light inside the fiber. It's carrying a radio wave, which is one of 7 forms of light. So yeah, fiber optics is much better than copper wire. Without fiber optics, we couldn't have computers, all right, or we couldn't have the internet anyway. But I'll talk about that when the time comes. Okay, getting back to superconductivity, that's a thing where resistance is equal to 0. Okay, all right. Anything else? Fiber optics is kind of getting away from the notion of electricity. It's kind of a different subject in physics. So, but we will talk about that. At least I certainly hope so. All right. Okay. Let's see. So silver is the best conductor, followed by copper, followed by gold, followed by aluminum, and then I don't remember. I'd have to look it up. Okay. Other things affect resistance as well. Length does. A longer wire, more collisions. You know, the longer the wire, the more collisions it's going to have, and so the resistance is going to go up. Temperature, if the wire is hotter, that means the atoms are vibrating more quickly. Okay, and if they vibrate, the atoms of the conductor are vibrating more quickly. Well, if they are, they're going to get in the way of conducting electrons more often if they're moving quickly. Okay, so the hotter they are, the more resistance it has. I don't know that it's linear. I don't remember if it is or not, but as the temperature goes up, the resistance goes up. Conversely, if the temperature goes down, the resistance goes down. And so if you put if your batteries are getting weaker and you put them in the freezer, you can eke out a little more electricity because the resistance inside the battery, if it gets cold, the resistance goes down inside the battery. So you can get a little more out of it. Okay? Doesn't work for long, but it'll get you a little more. So put your batteries in your freezer, you can get a little more out of them. And then finally, cross-sectional area. This is analogous to the width of a hallway. If a hallway is very narrow, you have a bunch of people standing in it, it's kind of hard to get through. But if that hallway is very wide, then it's easier to get through. There's more room to maneuver. So as the cross-sectional area of a wire increases, its resistance goes down because it's easier for the electrons to travel through. And I thought the videos I thought these videos, some of them, particularly the fun one, they did a nice job of that, I thought, in here. So yeah, and these videos I thought were pretty good as far as answering these questions. Okay, there you have it. Electricity worksheet 1. Questions, comments? Further? All right. Well, today, the real topic of the day is electric circuits. Okay, and there are two basic kind of circuits that we're going to talk about. Okay, and we're just going to go with the very basics. I'm not going to get too far into it. One is called a series circuit, and the other is called a parallel circuit. Okay, and I'm going to show you, first of all, I'm going to show you a schematic diagram of each, and then I'm going to a schematic diagram, and then I'm going to wire them up on the table in front of me. Okay. So the schematic diagram, which is a diagram that electricians use, electrical engineers use to represent circuits. Okay, for a series circuit, it's going to look like this. I'm going to have a battery. Okay, that is the schematic symbol for a battery. Okay, and a battery has terminals, positive and negative. The longer line is the positive terminal. The shorter line is a negative terminal. And then we're going to have a switch, and a switch is represented by that. Okay, and then we're going to have a couple of light bulbs. I'm going to have 3 light bulbs, and a light bulb is the schematic symbol for a light bulb is this. Okay, and I'm going to put another one over here, and I'm going to put another light bulb over here. And then I'm going to connect them with wires, and wires are just lines. Okay. Wire there, wire there, wire there, wire there. And this is the schematic diagram of a series circuit. Okay. Okay, so let's wire this up. So now I'm going to change cameras to my webcam. All right. Okay, so I have it in front of me here, and I have a battery. All right, I've got a battery here, and I'm going to try to when I do this, I'm going to try to put it the same way as I have it there. All right, I'm going to try to symbolize it the same way. So I'm going to put the battery over here. All right, and I don't honestly have a switch. There were no switches here when I started working here, and I have yet to purchase them. So give me a little while for that. So the switch, I'm just going to have a connection to the battery. So I'm going to put a light bulb over here, okay, light bulb over there, and a light bulb over there. I'm going to try to make it look like the schematic as much as I can. Okay, all right, and then I'm going to connect these with wires. So I'm going to connect the battery, okay, to the switch, which would be over here. But I'm going to pretend that the switch is between this and the battery. Okay, and I'm going to connect that light bulb, and then I'm going to connect wire to this light bulb. Like that. Let me get a little better connection over here. There we go. And then I'm going to connect this light bulb to this light bulb. Right? Because that's what we're doing. That's what we're doing in the schematic. So I'm going to connect the battery to the switch, which honestly is the light bulb to light bulb to light bulb, and then back to the battery. Okay, so that's what I'm kind of wiring up here. All right, and one more connection to make, and that's with the light bulb to the battery. And then when I close the switch or make the connection, when I make the connection, okay, light bulbs go on. All right, and this is a series circuit. Okay. Now, what's going to happen when let's get this a little bit more on camera. Sorry. What's going to happen when I unscrew this light bulb? Well, I don't know. Oh, both the other light bulbs went out. Okay. All right. What about if I unscrew this one? If I unscrew this one? Oh, they go out. No matter which one I unscrew, okay, they go out. And that actually makes sense if you think about it, because looking at my schematic, okay, the electrons want to come out of the battery and work their way around to the positive terminal. And if I unscrew any one of the light bulbs, there's like an open bridge. They can't get across. Okay, so it cuts off the path. And that'll be true of any of the other bulbs as well. All right, so if you unscrew any of them, it cuts off the current completely. Okay, and that's a series circuit. All right. Okay. Take off. Open the switch. The second kind of circuit that I'm going to have is called a parallel circuit. Let me stop. Let me change cameras again. And so I'm going to have a parallel circuit. Parallel circuit. A parallel circuit looks like this. I'm going to have a battery once again. Okay. Positive terminal, negative terminal. Right. If I had a switch, I would put it here. And then I'm going to put the light bulbs like this. Okay. And then I'm going to connect them. I'm going to connect the battery to the switch. I'm going to connect the switch to the first light bulb. Okay. The first light bulb to the second light bulb, the second light bulb to the third light bulb. I'm going to connect the battery to the first light bulb to the second bulb to the third bulb. And this is going to be my parallel circuit. Okay. All right. Well, let's wire this up. I'll change cameras again. I'm going to take everything apart. Take everything apart. Okay. And let's wire this up. My switch is going to be here once again. But I'm going to put the light bulbs in parallel like that. Okay. And so the switch is right here, imaginary. All right. So light bulb, battery to the switch, switch to the light bulb. And then first light bulb, the second light bulb, second light bulb to the third light bulb. All right. Like this. Okay, so now I got this going on. Okay, where I have battery to the imaginary switch to the first light bulb, to the second light bulb to the third light bulb. Now I'm going to do this part, the battery to the first light bulb, and then do that. Okay, so now the battery, see on camera, battery to the first light bulb, like that. Okay, first light bulb to the second light bulb, that, and then third light bulb to third light bulb, or second light bulb to the third light bulb. All right, and then I'm going to close the switch. All right. Now, notice that the light bulbs are brighter than they were before. Huh. Well, there's a reason for that we'll talk about after you do the lab. Now, what's going to happen if I unscrew this light bulb? Well, let's find out. Oh, the other light bulbs stay on. Huh. Why is that? Well, so I unscrewed this light bulb. But notice when I do that with a closed switch, let's just close that switch. Now, the electrons still have a way to get around that circuit to the positive terminal. Okay? So cutting off one path doesn't cut the entire path off. Okay? So if I unscrew that bulb, the other ones stay on. What if I unscrew the middle one? The other ones stay on. If I unscrew the third one, other ones stay on. Okay? That is characteristic of a parallel circuit. Okay? All right. Open the switch, and I'll take this apart later. Now, what you guys are going to do, I'm going to have you do a lab, and it'd be, if in a normal year you'd be doing this with real equipment, but I can't do that this year for obvious reasons. So what I'm going to do instead, we're going to do this in a computer simulation. All right. So if you, I'm going to share the screen now. Sure. Now, minimize this. Now, if you go to the, get my toolbar out of the way. If you go to the this week's Schoology folder, okay, and you, there we go, and you open and you go to the bottom. All right, there's a series in parallel circuit computer lab. I have it as a PDF, okay, like this, that you can download and print. Or if you wish, I will take this as a Google Doc. And so you can get that in here. Okay. You'll have to it's a PDF with a link to it. So you'll have to download this. All right. You have to download it. All right. Download. And then open it, and then it'll take you to, oh, okay. I guess you didn't have to. And then you can make a copy. And when you make a copy, okay, be sure to put your name on it. If you're going to do this, okay, just say, put your name in here. So this will be, come on, computer, respond. Put your name in there. So when you submit it, I know whose it is. And then when you access this link, it's going to take you to here, okay? And here is where you can wire things up. So for example, let's say I wanted to wire the first circuit down here, figure 1, okay? And it says, hook up the circuit in figure 1 below using 2 light bulbs and a pencil in series as shown below. So I have a couple of light bulbs, a switch, a battery, a pencil, and a voltmeter, something to measure voltage. Okay, well, let's wire this up. So what do I need? I need a battery. So I'm going to take a battery. I'm going to pull it in here. I'm going to rotate it up like that. I need a switch. Okay. And once again, I'm going to try to make it look like the diagram. So I'm trying to make it look like this. So I have the battery there, the switch there, the light bulb there, another light bulb there, pencil down there. So, okay, light bulb. Here's a light bulb. Put it right there. Okay. Another light bulb I could put right there. Okay. And then a pencil. You'll have to scroll down. You'll find it eventually. There it is. Pencil down there. All right. And then I'm going to connect these with wires. So the battery to the switch, I'm going to connect with a wire. So battery to switch. And then, okay. And this look at switch to light bulb to other light bulb, other light bulb to pencil back to the battery. Okay, so I'm going to take a wire, I'm going to connect that like that. Oops, like that to there. Okay, there to there. Pencil to the battery. And once I close the switch, okay, I get current flowing. Okay, you can see the light coming out of the light bulb. Electrons are moving real slowly, very slowly, okay? And then what we want to do is we want to measure the voltage. So I want to bring a voltmeter in, okay? So, oops, those are over here. I have a voltmeter or an ammeter, okay? Something to measure voltage or current. I'm bringing the voltmeter in. Notice they have probes, okay? and I can just touch the probe to the sides of, for example, the second light bulb, okay, or the first light bulb. No, we're going to end up measuring the voltages. Let's see, just measure the voltage across each light bulb, the pencil, and across the battery. Okay, so I'm going to measure the voltage, and the way to measure the voltages is just by touching the probes to each side. Okay, all right. Oh, yeah. Notice that it says -2 volts. The reason it says negative is because the red is positive. The red lead is positive. The black one is negative. The brown side of the battery is actually positive. So I should probably switch these. Okay. And then the voltage is now positive, 2 volts. Okay. Although honestly, if it doesn't really matter if it's negative sign. If there's a negative sign, that means you just got these switched, but it doesn't really matter. Just ignore the negative sign. Just ignore it. Okay, so just 2 volts for that. And then you can measure the voltage across each thing. All right. Oh, I don't have a contact. Oh, there we go. All right. In that case, 5 volts. And across the battery. Okay. And then put them in these blanks. All right. Then move on to series. Then highlight which statement, either the voltage across each resistor in general, anything that has resistance is called a resistor, be it a light bulb or a pencil or a computer or a hair dryer or anything. This is the general symbol for a resistor, a squiggly line. Okay, which statement is correct? The voltage across each resistor equals approximately the voltage across the battery, or the sum of the voltages across the individual resistors equals the voltage of the battery. One of those is going to be true. Highlight which is true. Then move on to number two. The task for this part is to measure the current at different points in the series circuit. So we're going to wire up figure 2. Now, the only real difference is we don't have the voltmeter, so I'm going to take the voltmeter away. All right, I'll put it away, and we'll get the ammeter in here. Now, where are we going to put the ammeter? Well, according to the schematic, I put the ammeter between the battery and the switch. Okay, I want to put it between the battery and the switch. So I'm going to cut this, all right, pull that out of the way a little bit, get that out of the way a little bit, and then we're going to put it right here, okay, between the battery. Let's open the switch while I'm doing this, and then put it between the battery and the switch. And then we close the switch, and we get a certain current going, okay? All right, that's the current for there. All right, then we're going to open the switch, and there'll be a place to record this down here. Then we're going to put the battery, let's see, record the value for the current for I1. Then put the ammeter between the light bulbs. Okay, so then we're going to cut it out of here. All right, we're going to cut that connection. All right, and we're going to put it between, reestablish that. And then we're going to cut that, and we're going to put the ammeter between the 2 light bulbs. Guess I need another wire. Okay, and then you're going to close the switch. I'm not going to do it because I'm going to let you see what happens. All right, and then put the ammeter here, and then put the ammeter here. Move the ammeter around the circuit and see what happens to the current. Okay, so you're going to be, for a series circuit, you're going to be measuring voltages and currents. All right, then you're going to do the same thing for a parallel circuit. You're going to measure voltages and currents for a parallel circuit. Okay, all right, this whole thing should take you about a half an hour, about the time remaining. All right, this and the cost of power assignment are due at the end of tomorrow. Okay, the cost of power assignment you should have, that'll take you about 15 minutes to do. That won't take you very long to do. And then this won't take you very long to do either. And then there's a place in Schoology to submit it. You can either submit the PDF or share the Google Doc with me, share the Google Doc, and I'll put it in Gradebook. They don't have to be correct. I'm going to show you what you should have gotten later, but I want you to get a little experience wiring these up. And I want you to do this on your own. A lot of times what happens, if you do this in a lab group, or if I put you in a breakout room, one person would be doing all the connections, and that would take away the experience from other people. If you're in here doing this with actual equipment, I say, okay, one of you wire this circuit, who's going to wire that circuit, who else is going to wire that circuit, who else is going to wire that circuit. Split up the work so that each of you get experience. So I'd like you to work on this on your own, okay? You can share results, but I want you hooking it up by yourself, okay? All right, I'm going to give you the rest of the time to do that, all right? So you have the rest of the period to work on that computer lab, all right? We're all going to stay in main session. If you have a question or you want some help, we can go to a separate breakout room and I can help you with that. All right. All right. Questions before, any general questions before you go? All right. You have the rest of the time to work. I'm going to stop recording.